Okay, folks.
Uh,
Yeah. You have a question? Okay, folks. Let's get going. So today we're gonna continue our discussion of partial waves. Actually, we're gonna finish it off today. So the end is near. And so and I'll give you an example today too. So partial waves, we'll talk about the importance of the range of the potential, and we'll give an example, an experimental example. Of these concepts. So maybe that will make it a little more clear too. Okay, so let's just remind ourselves what we're talking about. And so for partial waves, just to sort of remind us of what's going on, let's just remember that, you know, the whole point is we're solving the Schrodinger equation. The Hamiltonian is the kinetic energy plus some potential, where that's a spherically symmetric potential. And if that's the case, then we know that then we know that the eigenstate of the eigenstate of the Schrodinger equation, the solution of that equation is this. It's going to be some radial part times some spherical harmonic. And then we know that if we take the for a free particle, we know that the radial component is the Bessel function, the spherical Bessel function. And we know that for if we have a not free particle where the potential is not zero, then we know that the limit as we go away from the origin, we know that the limit of that eigenstate for any spherical potential is going to look like the Bessel function shifted, just shifted by phase shift. And so that's the phase shift. The most important thing, the phase shift. And so we can see it graphically by just plotting it, the radial part of the wave function. We see that for a free particle, it looks like this. It didn't draw it very well, but close enough. That's for the free particle. But if I turn on a potential, there's a attractive potential, negative V naught, that has some range, R naught. Then I see that the wavelength will get shorter. So I'll get more oscillations in this region. But as soon as I leave the potential, I'm a free particle again. And so my wavelength is constant, just determined by the energy. And so then this then is the phase shift that we're talking about. So the particle is, the radial wave function is shifted. So that's for the not free particle. When the potential is not equal to zero, then the wave function is phase shifted. So that's what we're talking about. And so if we can figure out, so then if we find those phase shifts, then the phase shifts are so important, because once we have the phase shifts, then we see that the scattering amplitude can be written in terms of the phase shift. 1 over k L equals 0 to infinity, 2L plus 1 PL cosine theta e to the I delta L sine delta L. And the total cross-section is this really pretty little formula that everybody likes. It's so simple to write. L equals 0 to infinity. 2L plus 1 sine squared delta L. So it's a sum over the partial phase, over the phase shifts. The cross section is the sum over the phase shifts. I mean, it's a sum over angular momentum, where the important thing you put into the sum is the phase shifts. So then the bottom line is then the whole strategy of the partial wave analysis is the whole strategy, if someone says to you, you know, here's some potential, what's the differential cross section, then what you do is you solve the Schrodinger equation in spherical coordinates. That's the key. And you find the radial wave function for some given angular momentum, and you take the limit as r goes to infinity, and that thing is going to look like a spherical Bessel function plus a phase shift, and then you just pluck this out, pluck it out. Then that's what we did last time in an example in class. We did an example. We solved the hard ball scattering, and so once you have plucked out the phase shifts, then it gives you the scattering amplitude. It gives you the differential cross section, because that's just the scattering amplitude squared. It gives you the total cross section too. Now there's an important point for these all this phase shift stuff, and you've already seen it a little bit, and I alluded to it last time. And the important point is that we only need to utilize a few angular momentums. So we typically only need a few L's in the sum, because you see that all of these are the most important results from partial wave analysis. And so there's a sum over all the angular momenta, but the point is that in that sum, we really only need to use a couple typically, or maybe only one. And then in particular, for low energy scattering, then only L equals 0 matters. And so that makes it even simpler. That's why we like the partial wave analysis. It really simplifies things. We only really, for low energy scattering, we only need to know the L equals 0 phase shift. And so what does that mean? What is the low energy scattering? Well, low energy, the definition of low energy, because it's always like low energy compared to what? Well, low energy is when K times R naught is much less than 1, where K comes from the energy, and R naught is the range of the scatterer, range of the scattering potential. And so then you can see that this is equivalent to K is 2 pi over lambda R naught. So that's 2 pi R naught over lambda less than 1, that inequality. And so that means that low energy means that the wavelength is way bigger than the range of the potential. And so that's your de Broglie wavelength, the wavelength of your particle. And that's the size of the potential. So that's what low energy means. It means you have big, long wavelengths and little itty bitty scatterer. And in that limit, then only the L equals 0 phase shift matters. And so why is that? So only L equals 0 phase shift matters. So the sum from L equals 0 to infinity turns into just L equals 0 component. You only need to worry about the L equals 0 component. So this we don't have to worry about anymore. Okay, so why is that? That's what I want to. That's what I sort of want to explain right now. Why that is. And so to understand that, what we have to do is we have to take a look at the Schrodinger equation to understand why only the low angular momentum components matter. We have to take a look at the Schrodinger equation in spherical coordinates. And of course, we know that psi is equal to REL times YLM. And so we really only need to worry about the radial Schrodinger equation because the angular part is easy. That's just a spherical harmonic. And so the radial Schrodinger equation looks like this: negative h bar squared over 2m 1 over r squared ddr r squared ddr of r el plus the potential plus some other stuff, h bar squared L times L plus 1 over 2m r squared times r equals E times r. Okay, so that's the radial Schrodinger equation, and you guys have solved this last semester to do the hydrogen atom. You did it, and maybe you did free particle and some other spherical potentials. And so let's, for a free particle, this thing is the often referred to as, it's an effective potential, often referred to as a centrifugal barrier. And this, it turns out, is really important, this term. And that's sort of like a confusing term because it's like when you do the Schrodinger equation and the radial equation, suddenly this weird term pops out, this 1 over r squared term, and it's added to your potential, so it's an effective potential. And you've all seen it before. And so if I have V equals 0, free particle, then you can see that your actual potential, your total potential, where this, I can think of this as my total potential, this whole term in the parentheses, then we see that only the centrifugal potential is left. And so the Schrodinger equation looks like there's a potential. Even when there is no potential, you still have this effective potential. So this effective potential is left. Even when there's no potential for a free particle. So a free particle experiences this potential, this weird effective potential. And so what the heck is it? Well, I mean, the way I like to think of it is it's actually a familiar thing, because it's sort of like if you're standing there and you're spinning and you have a rope and there's a rock at the end of your rope and you're spinning it around because there's some giant soldier who's going to come at you, so you got to hit him with that rock. Spin it around, you got to hit that guy with the rock to save yourself. And so I think you've all done this. You've all spun a rock around, and what you've noticed is that suppose you are spinning the rock and then you pull the rope, and now the string gets shorter and shorter. Okay, so you're just changing the radial component of the rock. What happens? tell me. I know that one of you has done this, probably all of you, or have done some kind of similar thing. What happens? Because I'm sure that you've all had to protect yourself from soldiers coming at you, and all you had was a rock on a string. Okay, so tell me what happens?
The rock's gonna spin faster.
Yeah, and when you pull it, do you feel the resistance? Is it hard to pull? Like, let's say you start pulling it closer and closer, you know, to you. Do you feel the resistance?
Yes.
That's right. And as you pull it, it gets closer and closer. It's spinning faster and faster, and the resistance goes up. It's harder to pull it because it's going whoa, 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 really fast. Okay, that's the centrifugal barrier. So you've all felt it. That's it. That's what we're talking about. Because you're pulling the rock closer, and so to conserve angular momentum, it has to go faster and faster. But a rock that's going faster has more kinetic energy. So you're basically pumping energy into it to pull it closer. Do you see what I'm saying? So that's the centrifugal barrier. So that means it's harder. If the rock has angular momentum and is spinning, then to pull that rock closer, it has to it's hard. It has to overcome the centrifugal barrier. That's what I'm talking about. And so this is this equation that I've written down here is the quantum mechanical equivalent of that process. So it's actually a familiar process to you. And so what that means then is that and that's what the radial wave function is just describing that rock. You know, what's the probability of that rock to be closer to you and further from you? The rock has some angular momentum, it's spinning. And what's the probability for the rock to be far away? And what's the probability for the rock to be close? And the point is that it's easy. The rock is happier to be far away because then it's going slower. If the rock comes closer to you, it's going faster. And so it's not as happy. It costs more energy. So that's sort of the dynamic that's occurring here. And that dynamic is all expressed in the centrifugal barrier, this potential, because it's a potential energy, an effective potential energy. And even when there is no other potential, even when there is no potential in the problem, that energy is still there. You know, to conserve angular momentum, the rock has to go faster when it gets closer to you, even in the absence of any potential. Okay, so what that means then is that if you plot this effective potential, then you see that let's plot it. Like, for example, let's plot it for this V effective as a function of R. Let's plot it for L equals 1. It's just 1 over R. Woo. Okay, that's what it is for L equals 1. I just plotted it. I'm just plotting this function. I'm just plotting this function, and it's just a 1 over R potential. Now, if my particle, and so now, but if my particle has some energy, E, then that means that you know from the Schrodinger equation that if the particle is on the right-hand side, I'm going to call this region 1. I'm going to call this region 2. What does the wave function look like in region 1? What does the radial wave function look like, just intuitively? And maybe I'll ask it even more simply. Is it wiggly or is it dying exponential? Which one?
Should be sinusoidal, right?
Yeah, because the energy is greater than the potential. And in quantum mechanics, when the energy is greater than the potential, the wave function is wiggly. Exactly. Wiggly. Okay, now how about region 2? Because in region 2, the energy is below the potential. What does the wave function look like in region 2?
Is it bound?
Decaying exponential.
It's a what?
A decaying exponential.
Exactly, because that's the classically forbidden region. And so the wave function goes, it goes to 0 very quickly in that region. So what that means then is that if you're spinning your rock, and your rock, you have some particle, and the particle has some energy and some angular momentum, you know, and those are the important things. Like, remember up here, you're right? You know, energy and momentum. You know, when we're talking about a radial wave function, the most important things are energy and angular momentum. So if the particle has energy and some angular momentum, let's say it has L equals 1 angular momentum, then that means that the rock does not, the particle cannot really come closer than this point. I'll call this R closest. That's the closest approach. Now, of course, that's approximate. You know, because it does have some decay constant, but let's just assume the decay constant is really fast. All right, just to make the discussion simpler. And so that means that the point of closest approach is when energy equals what? Tell me. The point of closest approach is when energy equals what?
The potential.
Potential?
Yeah, which potential?
The effective
Effective potential.
Yeah, the effective potential, exactly. H bar squared L times L plus 1 over 2m r closest squared, 2m r squared. And so I can then solve this, and I can, so I can take this equation and I can solve it for r closest. And what I can do is, notice that L times L plus 1 over r closest is equal to 2me over h bar squared, right? I'm solving this equation. What is this? It's our little friend. What is it? Oh, and this is squared. I'm sorry, squared. What is this that the arrow's pointing at, that expression? What is it? You've seen it.
K squared.
Yeah, that's right. Now, let's just, to simplify this equation, let's make an approximation. L times L plus 1 equals L squared. All right, just, let's just make an approximation because I just don't like to deal with L times L plus 1. It's just a pain, and it's almost L squared. So then that means then that we have L squared over R squared closest equals K squared. And so that means then that R closest is equal to L over K. So that means that the closest that the particle can really get is the angular momentum divided by K. And that's an important insight. What does that mean? That means a lot. That's really important. That's the whole point. Because now if I plot this stupid effective potential as a function of R, you see that I have the L equals 1. First, I ask you, what is the centrifugal barrier for L equals 0? What does the potential look like when when the rock has no angular momentum? What is the barrier then? What is this effective barrier when the rock has no angular momentum? What is it?
Just 0.
It's 0, yeah. So the particle can go right to the origin. It can go all the way in because there's no spinning. There's no, it's not like that rock on a string. And so, but as soon as you give the rock some angular momentum, suddenly there's a barrier. Now, if it has a little bit of angular momentum, L equals 1, it can get pretty close. Let's say that this is the energy. It can get this close. But notice that this effective barrier depends on L times L plus 1 in the numerator. So if I plot it out, it looks like this. This is L equals 2. This is L equals 3. This is L equals 4. Do you see the point? That as the angular momentum is bigger, then the particle doesn't get as close. The particle is forced to stay further away from the origin, see? So that will be R close for 1, R close for 2, L equals 2, R close for L equals 3, etc. So the particle gets pushed out further And this is something that you actually saw before, because check it out. You saw that the limit, you saw that I can write the Bessel function JL of KR is approximately equal to sine of KR minus L pi over 2 over KR. Remember that formula? We used it. You probably always wondered, what the heck is this thing doing here? You probably wondered about it for like 6 seconds, and then you just said, screw it, who cares, right? That's what I would have done. But now suddenly you realize that that factor is the important factor, because that is a shift. That is all the physics I'm talking about right now is right in that little factor, because that little factor is a shift. That L pi over 2 shifts you in which direction? I'm asking you a question now. That is shifting the sine function in a direction. What direction?
The right
Right.
direction.
To the right. That's exactly right. So you can see that if I plot, for example, J sub L, J sub 0, then it actually looks like this. And if I plot J sub 1, it looks like that. But if I plot J sub 2, it's going to look like that. And if I plot J sub 3, it's going to look like that. And if I plot J sub 4, it's going to look, see, the Bessel functions are getting pushed out as you give them more angular momentum. And that's what I'm talking about. It's this effective potential that's pushing out the radial wave function, because the Bessel function is the radial wave function. So all the physics is there, it's in it. Okay, well, that's important, because what that means then is that suppose that my potential has a range, equal to R naught. Then a question I would ask you, and I'm going to rewrite this equation. Remember that R closest is equal to L over K. We derived that equation. And so I'm going to ask you, this is my question to you, what is the highest angular momentum? What is the highest L that allows the particle to feel the potential? Because you see from this little drawing I've done up here, you see that as we increase the angular momentum of the particle, it gets pushed further from the origin. So like, look at this J4, this one I drew here. Look at that. Suppose that I had a potential right here. Suppose that was my potential, minus V naught with some range R naught. You see, the particle with angular momentum equals 4 doesn't even feel that potential, because the wave function is 0. It's 0, 0, 0, then boom, it gets big out here. So what that means is that if the particle has L equals 4, it doesn't even feel the potential. But if it doesn't feel the potential, what would be the phase shift? If I had this kind of situation where the particle doesn't even reach the potential, then what is going to be the phase shift due to the potential on the particle having that angular momentum? What would be the phase shift? Tell me.
Is there no phase shift?
That's exactly right. Exactly, the phase shift would go to 0, because if the particle doesn't feel the potential, there's no phase shift. And so now I'm asking you, what is the highest L that a particle can have and still feel a potential if the potential has a range R naught? I would say that I have range R naught, I have my maximum angular momentum, and what is the relationship between R naught and L max? Can you guess? It's just sitting right on the page. What is the relationship between the range of the potential and the maximum angular momentum that feels that potential?
Is it
Is
L
it-
max must be less than or equal to K R naught?
That's exactly right. Let's write it out. It's R naught is approximately equal to L max over K. It's this, because the closest approach is L over K. And so if I have some L, we need the L can only be big enough so that its closest approach reaches the range of the potential. If the L is bigger than that, it won't reach it. And so this is the relationship. It's this. R naught is equal to L max over K, in which case it's just what you said. K R naught is equal to L max. So the maximum angular momentum is K R naught. L max equals K R naught. So that means that when you do your sum, sigma is equal to 4 pi, your beautiful little sum, K squared, L equals 0 to infinity of whatever is that little equation that we painstakingly derived, 2L plus 1 sine squared delta L, yeah. 2L plus 1 sine squared delta L. That means that for this sum, for the cross section, I don't need to sum all the way up to infinity. I only need to sum up to what? Tell me. Tell me.
L max?
Yeah. Where L max is equal to K R naught. So now what happens? Now suppose I have a low energy. Suppose I have low energy. Well, that means that low energy is defined as K R naught is what? What's the definition of low energy? K R naught is what? What's the definition of low energy?
So much less than 1.
That's right. And so if K R naught is much less than 1, then what can I say about L max? In the sum.
Much less than 1?
That's right. And how many L's are there less than 1? How many? Tell me.
There's no L, right?
Well, actually there is. How many? Oh, maybe that's what you meant. No L. Well, there is an L. It depends on like how you how you define that. There is one L that's much less than 1. What is that L?
Is it just the L equals to 0?
That's right. Because L is quantized. L is quantized. It's 0, 1, 2, 3, 4, 5. And so L max then is 0. And so in the low energy, so in the case of low energy, L max is 0. And so that means that only your L equals 0 phase shift matters. And then we say that sigma is equal to 4 pi over K squared. The 2L plus 1 just turns into 1. It's just going to be sine squared delta naught. Okay. And so this is so that's why this phase shift treatment is so powerful, because it really simplifies the picture. You really only have to deal with a couple of phase shifts, and sometimes only one phase shift. Okay, let's do an example.
Can I ask a question really quick?
Yeah,
before
of
we move
course.
on?
Yeah.
I'm a little confused. So we did this treatment, but like we only looked at like the J equals 4, or like the J4 one where it actually is shifted. So like, does this apply? Like, I don't understand. Does this apply to like every different L value? Or I'm a little confused how we even, like, I don't know. I might be getting a little lost.
Okay, yeah. So the reason why I showed it So here I'm showing it right now where the arrow is pointing. Now, the
Yeah.
reason I drew that was to just give you like a tangible example, just to show you that if you literally plot, like take Mathematica or MATLAB or your favorite plotting program and just plot Bessel functions, and you'll see that as you increase the angular momentum, the L value, then the plot of the Bessel function is pushed out. It is literally pushed out. And that's what I was expressing here with those drawings. And so here I was trying to give you, by these drawings, I was trying to give you an intuitive feel that the free particle, as you give more angular momentum to the particle, a free particle is pushed further from the origin. The free particle, as you give it more angular momentum, the free particle cannot go to the origin because the wave function has no amplitude there. You know, it goes to zero. You see, that's what I was trying to draw here. I don't know if I did a good job.
Oh, gotcha. Okay.
That's what I was trying to express within these drawings. But in terms of equations, these, and so the question is, so you can just see from the drawing that each of these has a closest approach. See?
Yeah, yeah. Oh, okay, I see. And so we just found which L it really matters, and so that's like the 0 or 1.
Yeah, because here I should draw it here. Like this is the for this one, that's the R closest for this L equals 4.
So when you say, well, in this case, we only show that you only need 1. That's L equals 0. But like, what would need to change for you to need like L equals 1 or L equals 2 as well?
It's right here. Check it out. It's this formula that we derive right here. I'm circling it. See, L max is KR naught. And so your sum goes from L equals 0 to L max, where L max is KR naught.
Oh.
So if KR naught is 3.2, then I would sum up to 3.
Gotcha. Okay, that makes sense.
And suppose, so for example, this is actually a cute little point. Like, check this out. When E is low and L max is 0, then we call that, it actually has a name. We call that S wave scattering. Because I only need the L equals 0 component, which is the S wave. S, like, you know, SPD, you know that, remember from last semester, SPD, like L equals 0 is S, L equals 1 is P, L equals 2 is D, right? You remember that?
Yeah.
And so this is called S wave scattering. Now I'm asking you, and I'll ask you a question, or whoever, you know, I'll ask all of you a question. Suppose that this KR naught was 1.3. So that means now we have to sum the phase shifts up to 1, okay? And suppose for some reason the L equals 0 phase shift was 0, but there was but the L equals 1 phase shift was important for some reason, you know, when you solve the Schrodinger equation, you know, who knows why. But suppose I had L equals 1, suppose the L equals 1 phase shift was dominant. What would I call that? I call that, for L equals 0, I call it S wave scattering. For L equals 1, what would I call it?
P wave scattering?
That's right. L max equals 1. I call that P wave scattering. Because the delta L equals 1 is important. And you could also then imagine D wave scattering, and that means the L equals 2 is really important. So people actually use these terms. Okay, so now I want to go to the example that I'd like to discuss with you, where we can actually do an example of this. I mean, we already did an example. I mean, you know, the hardball scattering that we did last time was an example, but now I want to give you an example and show you some actual experimental data. So what I want to do is I want to analyze a physical situation that people actually did experiments on, and then I'm going to actually show you data. All right, so now we're going from like the theory, you know, to the experiment, which, you know, actually doesn't get done.
Professor?
Yeah.
Can I ask one more question?
Sure.
For KR naught value, you said like for low energy, we could say R naught K is going to be much smaller than 1, but for other cases, how do we know what value we have for KR naught?
Oh, because
The
you know it.
restriction.
Because check it out. You know the energy. K is 2me over h bar squared, right? You know K.
Oh,
and
okay.
you know R naught. You know them.
Right. Okay. Yeah.
Okay.
That makes sense. Yeah. Thanks.
You can just divide them and see. So you can calculate K R naught. So K R naught is a known quantity. Okay. So let's ask a question. This is the question. This is the big question that people actually care about. Or, now we mostly know the answer, but well, it depends on the system. But this is a question that people actually care about. What happens when you drop an atom into a pool of electrons? What happens when you drop one atom into a pool of electrons? Okay, that's the question. And so let's refine the question. Let's just keep it into 2 dimensions. So because 2 dimensions is important, that's a very important dimensionality, 2 dimensions, because we often do things on surfaces and in ultra thin layers. So let's suppose we have a 2-dimensional pool of electrons. And what happens when we drop a single atom into that 2-dimensional pool? And so I guess the question is, what does it mean to ask the question, what happens? Because it's quantum mechanics, so every question needs to be thought about carefully. So let me refine that question. Now I'll say, what do you see? Okay, so what do you see when you drop an atom into a 2-dimensional pool of electrons? Okay, we refined it, but now I have to refine it a little bit more. What does it mean to see? Like that's not obvious. What the hell am I talking about? How do you mean? What does it mean? What do you see? This is all really tiny stuff. I mean, atoms are like way smaller than the wavelength of light. So it's not like you actually see anything. Because there's no, you can't see it with light because it's too small. It's subdiffraction limit. Okay, but what I mean is what I'm really mean is, what does the wave function look like? That's what I really mean. What does the wave function look like? But how do you see the wave function? Well, it turns out that we can see the wave function. What was that? Are you asking a question? Okay, well, it turns out that we actually do have a way of looking at the wave function. There is an experimental technique that allows us to look at the wave function, and that experimental technique is called scanning tunneling microscopy. And this is a technique that I use. So this is a technique that I am an expert at, scanning tunneling microscopy, otherwise known as STM. STM. So this is a technique that allows us to see the wave function and visualize the situation. So this allows us to see the wave function. Okay, and so let's do 2 things. Let's ask ourselves, how does the STM see the wave function? I'll explain that. And then let's ask ourselves, what do we expect the wave function to look like? What side do we expect? What expect side? That's a little bit not very understandable. What psi do we expect when we drop the atom into the 2-dimensional pool of electrons? And then the third, so let's answer each of these in turn, 1, 2, and then the third thing is, what do people actually see when they do the experiment? What happens experimentally? Because that's how science is done. You have an idea, you have a prediction, and then you do the experiment to test the prediction. What happens experimentally? So this is the prediction, and this is the test. Okay, so let's answer these questions in turn. Hopefully we have enough time. Let's answer question 1. How does the wave function see how does the STM see the wave function? Well, this is how it works. What the STM is a little needle, and it's hooked up to a piezoelectric transducer. That's called a piezoelectric transducer, which means that you put a voltage on it and it expands or contracts. And so this little piezoelectric crystal, by putting voltages on it, we can move this little needle around the tip with very fine motion. We can move it small distances much smaller than the diameter of a single atom. And let's not get into how that works, because that's not important for today's discussion. But if I put a voltage on the tip, and if I take a surface here, then I can pass current from the tip into the surface. Okay, and this current I can measure because I have an ammeter. I can measure the current. It's easy to measure current. Ammeters are cheap and easy to use. And so it turns out that what's happening is that the surface, the electrons in the surface have wave functions. So that's the wave function of an electron at the surface. And the tip also has a wave function. And the wave function of the tip, so I'll call that psi of the surface, I'll call that psi of the tip, and they overlap. And so the current, the electrical current that flows through the tip is proportional to that overlap squared. You know how it is in quantum mechanics, you always square everything, you know, to get the probability. So it's the overlap of that wave function of the tip and the surface that matters. And when you work through some equations, and I'm not going to do that, somebody else did it, and that's not important for today's discussion. I'll just give you the result. It turns out that the current that comes out of the STM that you measure, which is a function of position and energy, and this R is the position of the tip, and the energy is set by the battery. E equals charge of an electron times the voltage on the battery. So the position is the position of the tip. The energy is set by this battery. This, you know, that's the battery right there, battery. And then it turns out that the tunnel current is proportional to, and there's some constants that we won't worry about. It turns out that you have to do a sum over all the degenerate states at E, at the energy you're probing, and you take all those states, and it's a sum. I'll index the degenerate states with the variable K, although that's meant to be just, you know, it's meant to be any quantum number that describes the system. K and squared delta minus EK. And this is called the local density of states, local density of states, fondly referred to as LDOS to experts, LDOS. And it's really, you know, when you first look at it, you might think, oh, that looks confusing and complicated, but it's not. It's just, look, it's just psi star psi, okay? Psi star psi, which you guys all know, that's probability. It's just psi star psi, and it's just adding up psi star psi for all the degenerate states. And that's actually a very sensible thing, because, I mean, if I have an STM tip and I have a surface and there's all these wave functions at the surface, then, and suppose all these wave functions have the same energy, E, and I'm shooting electrons into the surface that have some energy, E, then my electrons can go into all of those states because they all have the same energy. So the electron goes into all of those states. so my tip can shoot electrons into all of those states. And what's the probability of that occurring? Well, it's just going to be psi star psi, right? And so I think it's kind of a logical sort of a thing. So it's just, I just add up all the degenerate states. So, so I is equal to the sum of all the degenerate states, psi star psi, of all the degenerate states at E. And E, the E is the energy you're probing, set by the battery. So okay, so that's all right. So that's how the STM works. And so now let's answer. So that was question 1. All right, how do we see psi? So that's how you see it. Because to see, then what to do to see psi of R, then you just measure I of R, okay? Because if I is proportional to psi star psi, then if I just map out the current as I move my tip around, then as I map out the current, then that's the same as mapping out the LDOS, which is the same as psi star psi. Okay, so I can take a picture of psi star psi, or literally a picture. All right, so now the question becomes, what do we expect that picture to look like? Let's derive that using quantum mechanics that we've been doing in class. So now let's answer question 2, which is, what does LDOS look like? For one atom in we call it a 2-deg, 2-dimensional electron gas. All right, a 2-dimensional electron gas.
Professor?
Yeah.
What was the psi k? That's the overlapping wave function?
Psi k.
In the current equation.
In which equation?
In that current is proportional to the sum of the degenerate state of E. Is that
This equation?
right?
Well, the point is the k is just meant to denote whatever quantum number matters, and you'll see that as I go into the example. I think the more important way to think of it is like this: is this equation. Let's look at it. Let's think of it like this: I of R E is equal to psi of R having energy E squared. Okay, maybe this is a nice way to think about it. Is that the current through the tip, when the tip is at the location, that's a tip location, and that's the energy of the electrons we're shooting in, E times V. Then the current that flows from the tip is proportional. I should keep that a proportionality. Is proportional to psi star psi at that location and for states that have that energy. Now, does that seem plausible to you?
So that's neither the wave function of the tip nor the wave function on the surface, but it's the overlap, or is it the wave function?
This is, well, I haven't told you how I derived this equation. So the way that people derive this equation, and I'm not going to derive it for you, because it's like this big giant thing to derive it. But basically what you do is it's here, it's the overlap, because when you calculate the overlap, you'll find that the overlap is proportional to LDOS. And the LDOS is that little equation right there. And the reason why it works out so beautifully is because there's one last atom on the tip. And that last atom on the tip, if you think of that atom as having a spherical wave function, then that last atom has an exponential spherical wave function at the tip of the tip. And so when you overlap that exponentially dying spherical wave function at the last atom on the tip, and when you overlap that with the wave function of the surface, then you get exactly this LDOS, because the average of that spherical exponential wave function overlapped with the wave function of the surface gives you the LDOS. Does that make any sense?
Okay. It's a little
So-
complicated, but
Well,
yeah,
I mean,
very
that's
interesting.
that's how you derive the formula. But I don't have time to derive the formula for you, but I just told you the derivation.
Yeah,
That is how
thank
you do it. Okay, and that was derived in, you know, not that long ago. I mean, that was derived in like 1988, you know, so this is not like 100 years ago, but it is a while ago. So that was a formula. This formula was derived in like 1988. So it's not like super old. Okay, and that's called the Tirsoff-Hammond formula. Okay, so now we're going to ask ourselves, what does the local density of states look like for a single atom in a two-dimensional electron gas? And so what we do is we, you know, here's the thing. It turns out that there are some surfaces support a two-dimensional electron gas. And that's another thing that I don't have time to actually derive for you, but I'll just assert it because it's true. And, you know, there's all kinds of reasons why it's true. It's like a whole field of study, but we don't have time to get into all those details. But there are certain surfaces that support a two-dimensional electron gas. And those surfaces, for example, are copper, silver. These are surfaces that you know, gold, beryllium. These surfaces all support two-dimensional electron gases, and you might not have known that. Probably, I'd be surprised if you did, actually. But it turns out that is certain crystallographic surfaces, like you take, these are, well, let's forget about beryllium. That one's a little bit of an outlier, but let's consider copper, gold, copper, gold, silver, copper, silver, gold. These are FCC crystals. And if you go to the what's called as the 111 surface of these crystals, then you get a two-dimensional electron gas. And it's due to all kinds of, and the reason for it is all kinds of fancy solid-state physics. And so if you want to understand that, you have to, like, you know, take solid-state physics. And then it's all, you know, the solid-state physics of it. But let's not get into that. Let's just run with this concept that if I go to the surface of one of these crystals, and here's the surface, that's the crystal, and here's the surface, then I'm going to have all these two-dimensional electrons running around. Okay, there they are. They're running around. Okay, and then they're, you know, and they're the wave functions are waves, right? E to the I k dot r. So I have all these two-dimensional electrons running around on the surface, and so now what I do is I'm going to drop an atom down there, and here's an atom. Boom, there's my atom, and so without solving any equations, you can already get a sense of what's going to happen. I'm going to have these two-dimensional electrons. They're going to go this way. They're going to hit that atom, and they're going to bounce off, right? And then I'm going to have some electrons here. They're going to hit that atom, and they're going to bounce off. And then that's going to give me some local density of states. And when I come in with my STM, that's what I'm going to see. I'm going to see that local density of states. And so that's what you should see. So, but what we want to do now is actually derive it, you know, using quantum mechanics. And you can already imagine what it's going to look like, because it's going to be like a standing wave. Because this guy going to the left looks like a e to the minus ikx, and this guy going to the right looks like an e to the ikx. And so you can see that when they add up, they're going to give me a standing wave, which is a sine kx. So you just intuitively. But let's not just do hand waving. Let's actually derive it. So let's derive the local density of states. And so before we do anything, let's derive the local density of states for a two-dimensional electron gas without the atom. So this is basically what happens when the STM is just looking at the surface of, say, copper, as an example. Let's pick copper. And so if we're looking at the copper and there's just a two-dimensional electron gas at the surface of copper without any atoms added to it, just the perfect surface, what do we see? Let's calculate that, because what we see is the LDOS. But the LDOS is equal to the sum of all the degenerate wave. We want to know what we're going to see at some energy. LDOS is a function of position and energy. And so that's going to be the sum of all the degenerate states at that energy, psi star psi, as a function of position. All right, so that's what we have to calculate. So let's calculate it. So we have a two-dimensional system. So let's use polar coordinates. And so to get the psi, the degenerate psi, we need to solve the Schrodinger equation, H psi equals E psi. Okay, because everything always comes down to the Schrodinger equation. So let's solve the Schrodinger equation for the two-dimensional electron gas at the surface of copper. And so that Schrodinger equation we got to pick a coordinate system, and it turns out it's easiest to do it in polar coordinates, cylindrical coordinates. So let's do polar coordinates, and so let's write down the wave function. Let's write down the Schrodinger equation. So the Schrodinger equation, is negative h bar squared over 2m del squared plus v of rho. So we'll do it in rho, and that's phi. We have two angles, rho and phi, in polar coordinates. And so we have a potential. This is the Schrodinger equation in 2 dimensions. We have psi of rho and phi is equal to E times psi of rho and phi. Now for a free particle, so without the atom, that means it's a free particle. That means there's no potential. So no atom means no potential, which means that V of rho equals 0. So that means we have, so that we can kill. And so that means we just have the simple Schrodinger equation. But it's not so simple because, when you write the del squared in different coordinates, it's a big pain in the ass. And it's no different here. So when we write it all out, it looks like this. Negative h bar squared over 2m. And in spherical and cylindrical coordinates, this Schrodinger equation looks like this. dd rho, dd rho, plus 1 over rho squared, d squared, d phi squared, psi of rho phi equals E of rho phi, psi of rho phi. Okay, so we got to solve that. And so what we're going to do is we're going to use separation of variables. And when you use separation of variables, that's basically saying that the wave function can be written as some radial function, which is a function of rho, times some angular function, I'll call it y, which is a function of phi. And so then we plug that in and we go through all the separation of variables stuff, which I'm not going to do. But when you do that, you can see that the y of phi, now in 3 dimensions, y of phi would be a spherical harmonic. But in 2 dimensions, it's easier. It's just e to the I L phi. And so it has L, angular momentum L. It does not have M because it's confined to 2 dimensions, because in 3 dimensions, the YL, you have YLM because you have 2 ways that you can rotate, but in just 2 dimensions, there's only 1 way you can rotate, so it's simpler. So that's the angular part, that's really simple, but the radial part is more difficult. The radial part looks like this. Let's write the radial part, radial. And the radial part is going to look like this, rho squared, d squared, d rho squared, r rho plus rho, dd rho of r of rho plus 2m over h bar squared, 2me over h bar squared rho squared minus L squared times R of rho equals 0. Okay, so this is one way of writing the radial equation. And it should look kind of familiar because that looks a lot like the rate. And I'm not going to write the radial equation in 3 dimensions, but we were just looking at it not too long ago. And you notice it looks a lot like this. And so I'm going to ask you, so it turns out that this is a famous equation. and it has a famous solution. Famous equations always have famous solutions. So does anybody know what this equation is? Can you guess what this equation is? It turns out it's Bessel's equation. This is Bessel's equation. And can you tell me what the solution is? Tell me.
Bessel's function.
That's right. It's the Bessel function. Now, there's a Bessel function, but there's two solutions. There's a second order equation, and so there's two solutions. So what's the other solution? Oops, I'm giving it away.
Neumann function.
That's right. Now, you should be slightly annoyed because you're probably thinking, wait a second, that's the same solution that we use in 3D. But that's not true, because in 3D, remember, we were using little j sub L of k rho. And here I have big J, because in 3D, it was a spherical Bessel function, which is a different thing. This is the actual Bessel function, because Bessel functions were derived for 2 dimensions, not 3. So the actual Bessel function is for a 2-dimensional wave equation, because Bessel functions were really are most famously derived when you have a drum. Like, you know, a drum, you go bung, bung, bung on the drum, and you ask yourself, how does the drum head vibrate when I hit it? A drummer? Like, what happens when you're in a rock band and you hit the drum with the stick? Well, a lot of rock musicians really wanted to know the solution of, you know, what was really happening, you know, because they're very, very curious people. And so the rock musicians solved the differential equation, and they found that the drum head vibrates, and the vibrations are described by Bessel functions. So that's really famous. That's where it came from. Okay, and so, but of course, the Neumann function diverges, and so that's going to go to 0. And so we see that the radial wave function is equal to the Bessel function, where the energy is living in the K, just like before. Okay, and so now we have the wave function, because now we see that the wave function, which is the wave function, the eigenstates, which are described by an energy and an angular momentum, and they are functions of rho and phi, they can be written now. There's some constant, a normalization constant in front, but we have them. This is what they are. And then I have an e to the I L phi, because there's a radial component and an angular component, just like before. But now it's in 2 dimensions. But that means that now we can find the local density of states, because the local density of states is just the sum of all the degenerate states of the wave function psi e L of rho phi squared. Now I'm going to ask you a question. What do I sum over? All the degenerate states at a particular energy. What do I sum over? Tell me.
At the surface?
Not exactly. It's a variable that I'm summing over. What variable?
Is it L?
Yeah, exactly. And I just, you know, it's like we've been dealing with this for like, you know, weeks, but, you know, I know that it's like sometimes hard to sort of see these connections. And because the point is that all of these different L's because we did, remember when we did the partial wave analysis, we summed over the L's, right? And the point is that even for a particle with one energy, all the different L solutions are degenerate. You can have one energy. See this equation? I mean, I'm writing it right here. You know, suppose that we fix the energy, but that means that I can change that L, because if I fix the energy, that means that I fix the K. If I fix the energy, I fix the K, but L is a variable. So basically I can have the L equals 0 solution, the L equals 1 solution, the L equals 2 solution, the L equals 3 solution. It's basically saying that I can have a rock spinning it with different angular momentum and it can have the same energy. That means because the rock could be close or it could be far or further or further. So that means like I can have a rock and I can have many different angular momentums and they can all have the same energy, just depending on where the rock is located. Okay, and so that means that all these different L's have the same energy. So the local density state, and now when I square it, what's going to happen to this term when I square it? The E to the IL phi term, what's going to happen to that? Tell me.
It goes to 1.
Exactly. And so the local density of states that we expect at the surface of copper should look like this. It should be a sum from L equals 0 to infinity, all the possible angular momentums, 0, 1, 2, 3, 4, you know, integers, of the Bessel function of K rho squared. That's it. Where K is square root of 2me over h bar. Okay, now it turns out, and this I'm not going to drive, but this is something you can look up in a book. It turns out that if you add this up, there's a mathematical relationship. It turns out that this is, and this is not obvious, but it's true. It's a constant. You can look it up. It's like, you know, pi or something. Who knows what it is? I can't remember. It's a constant. And if you think about it hard, you might justify that to yourself. But let's not let's not do that today. Let's just remember it's a constant. And so that means then that when I take a look at the two-dimensional electron gas without anything inside of it, what do I see? Tell me. We just derived it. What do I expect to see? This is my STM, and this is the surface of the 111 surface of copper. What do I expect to see? Tell me. When I scan around and you know, take a picture of it. STM sees LDOS, and what does the LDOS look like? We just derived it. What does it look like? Tell me. Tell me. What do I see? What is the picture? It's on my computer screen. I took a picture of it. What am I looking at on the computer screen? This is like a very practical question. Tell me, someone, what should it look like?
Would it just be like a flat line because it's a constant?
Exactly. It's sort of a trick question. What I see is nothing. There's nothing there. It's just a flat, exactly, just a flat surface. Nothing. That's sort of a trick question, but I wanted you guys to think about it. Okay, nothing. So that's pretty boring. Okay, but it's still important, you know. So this was my LDOS. Okay, now let's do the next thing. Now let's drop the atom, okay? And this is what we do. Now we have this situation, okay? Now I have an atom, one atom. Now this atom creates a potential, V of rho, okay? And that potential is localized. You know, it's pretty local to the atom, but electrons swimming around, they're gonna hit that atom, they're gonna feel a potential, and that potential will be, you know, cylindrically symmetrical, V of rho, okay? So now I'm gonna ask you, and let's suppose that we have low energy. Suppose that we're looking for it at low energy. And what energy is low means is that the wavelength of the electrons is long compared to the size of an atom. So let's suppose that we have a little atom and really long wavelength electrons, okay? That's the atom. We're in that limit. Okay. And the local density of states is this formula. The local density of states was this formula before. I have it right here at the top. So now I'm going to ask you, how does the local density of states change? Because the atom is there. And I'll help you with the answer. It's going to affect the wave functions that have certain angular momentum. If the angular momentum of the electrons is really high, will those electrons see the atom? Yes or no? Based on our previous discussion at the first half of this class today, if the angular momentum of the electrons is high, will they see the atom? Will they touch it? Will they feel it? Yes or no?
No.
That's right, they won't, because their wave function is pushed way out, away from the origin. They won't see it. So now we have really low energy electrons. They have a trouble coming in. So which angular momentum of the electrons will feel the potential at the origin? What angular momentum?
0.
Yes. If the angular momentum is greater than 0, will those electrons feel the potential? Yes or no? And I'll write a little formula to help you remember. Remember, L max equals K R naught. That's the range of the potential. And for low energy, this is way less than 1. So if the angular momentum is greater than 0, will those electrons feel the potential? Yes or no?
No.
Right, exactly. So that means that now our local density of states is very simple, because what happens is that all the wave functions are the same. The psi E L's are unchanged, except for one. Which one? L equals what? All the wave functions, all the eigenstates of the electrons at the surface are the same. They're unchanged. The atom doesn't change anything except for one angular momentum component. And which one is that? Say it.
0.
Yes. And so what that means then is that the local density of states that we see is the same as before, except we have the L equals 0 component, which is J0. That one is changed, and it's changed by the L equals 0 phase shift, because that's what happens. That's what the new wave function is. We know the wave function. It's just a phase shifted Bessel function, but all the other ones remain the same. L equals 1 to infinity. J sub L of K rho. Now let's do a little trick. Let's do a little math trick. And that math trick is, let's add 0 is equal to J0 of K rho minus J0 of K rho. And let's add it to this. And so then what we have is we have L DOS of RE is equal to J naught of K rho plus delta naught squared minus J naught of K rho squared plus L equals 0 to infinity of JL of K rho squared. Okay, do you see that? Just a little math trick. What does this guy equal to? I told you before, I don't know if you remember, but that's the sum of the Bessel functions from 0 to infinity.
Is that a constant?
Yes, constant. Now these guys, it turns out that I can plot the, we already, it turns out that in 2 dimensions, the Bessel function, if you go away from the origin, it has a very simple functional form, and it's equal to this Bessel function, the J naught Bessel function, is equal to square root of 2 over pi k rho times cosine of k rho minus pi over 4. So that's just an expression. That's what a Bessel function looks like. And so then here I square it. Well, I'm going to end up squaring the whole thing. And then this guy is going to look like the same thing. It's going to be square root of 2 over pi k rho cosine k rho minus pi over 4 plus delta naught squared. And so what we get then is this very simple little formula, which is that a prediction that the local density of states is going to equal a constant plus 2 over pi k rho cosine squared k rho minus pi over 4 plus delta naught minus cosine squared k rho minus pi over 4. Okay, a little formula. This is it. So this is what theorists do. Theorists do this kind of stuff all day long. They dream up a physical situation and then make a prediction. So we've just made a prediction what the local density of states should look like. Okay, now I'm going to click off because now I'm going to, now I don't know how to, let's see, let's stop the share. And now let's share this one again. Now let's look at the experiment. Okay, and this is an experiment that was done by me, actually, a long time ago, before you guys were even born. Enable editing. So here I show, can you see that?
Yeah.
Okay, so this is an STM image of an atom sitting on the surface of copper. Okay, and you see all those waves around it, all those rings. If I take a cross section of it, what you're seeing is a local density of states. We're imaging it with the STM using the technique that I described. And here's the cross section, the solid line. Now let's take that formula that we just derived a minute ago and fit it to this data, and that's the dashed line. And here's the formula right here in the paper. See it? Cosine squared k rho delta naught. And you fit it, and then you can even see in the caption, delta naught is minus 80 degrees. And that's a negative phase shift. That means that it's repulsive. So the atom pushed out the electrons and caused a phase shift of 80 degrees. And that's why it looks like that. And we're able to take a picture of it. Now that means that these rings that you're seeing are a reflection of the scattering of the atom, how it's scattering the electrons. Then what we can do, and the next thing that we did, was to take those atoms and put them into a ring, because now since they scatter the electrons, they can trap them. And so this is the eigenstate of a 2-dimensional electron trapped in a ring. So this is the quantum corral. That was the next thing, but we haven't talked about this in class. What we've really been talking about is this thing. This is what I wanted you to understand, because this is a perfect example of scattering in the context of solid state physics, but it's still, relevant. It's like a universal type of behavior. Okay, folks, that's it. Bye.